VMCG is short for the Ground Minimum Control Speed, and it is described for you in Cap 698 at the bottom of page 2 of section 4. It states VMCG is the minimum speed on the ground at which the takeoff can be safely continued when the critical engine suddenly becomes inoperative and the remaining engine are at takeoff thrust. Let's try and understand what this actually means. When an engine fails, the remaining engine still generates thrust, and this causes the aeroplane to yaw away from the live engine. The amount of yaw is a function of the amount of thrust the live engine is generating. Greater thrust from the live engine would generate more yaw. The only way to counteract this is to use the ailerons and the rudder to try and steer the aeroplane in the right direction. However, when the aeroplane is on the ground, you cannot use the ailerons to control the yaw, otherwise you might bank the wing into the ground. Therefore, the only available aerodynamic surface left to control the asymmetric yaw is the rudder. However, for the rudder to be effective at controlling the yaw, there must be sufficient airflow over it to ensure it has the required aerodynamic force. This minimum airflow speed over the rudder is VMCG. If the engine were to fail below this speed, then there is insufficient flow over the rudder to counteract the asymmetric yaw, and therefore it is not possible to continue the takeoff. The only factor that controls the value of VMCG is thrust, and since takeoff thrust is more or less constant, then the only variable on the amount of takeoff thrust generated is air density. The higher the air density, the more thrust can be generated, and therefore the more yaw that is generated when the engine fails. Therefore, the flow over the rudder must be faster to make the rudder effective enough to counteract the yaw. The effective air density on VMCG can be seen by looking at the second table from the bottom on page 18 and 19 of section 4 in Cap 698. This table shows the variable of temperature on one side and the variable of pressure altitude on the other. Look at the VMCG in the table and notice that at low temperatures and low pressure altitudes, where the air density would be high, the value of VMCG is also high. Therefore, we can say that as density increases, VMCG also increases. Although VMCA is the minimum control speed in the air, the factors that affect VMCA can, for the purpose of the exam, be the same as for VMCG. We stated that there were two particular speeds that can influence V1. One of them was VMCG, which we just discussed. The other was VMBE. Turning back to the top of page 3 of section 4 in Cap 698, you can see the description of VMBE. VMBE is the maximum brake energy speed, and it represents the maximum speed on the ground from which an aeroplane can safely stop within the energy capabilities of the brakes. Essentially, this means that if the takeoff was abandoned at a higher speed than VMBE and maximum braking force was applied, the brakes would not be able to safely bring the aeroplane to a stop, regardless of how much runway was left. The brakes would most probably catch fire, melt, or even disintegrate. You do need to be aware of the factors that control VMBE, but luckily, most manuals, and indeed Cap 698, has a VMBE graph or table with all the variables and factors on it that can affect VMBE. The graph concerned is on page 15 of section 4 and is shown on screen. Watch the demonstration on how to work through the graph. If you need to see the effect of a variable, for example mass, simply work through the graph but use two different masses, as shown here. In this case, the heavier mass has reduced VMBE. The variables that affect VMBE are pressure altitude, ambient air temperature, mass, slope, and wind. Carefully examine each of these factors, so you can see for yourself how they change VMBE. Remember, CAP 698 is for use in the exam, so if there are any questions which relate to VMBE, you can rest assured that a lot of information on VMBE is already in front of you. Having looked at VMBE and VMCG, we are now better placed to understand why these two speeds play a role in influencing V1. According to the rule, V1 must not be less than VMCG, as shown. V1 cannot be allowed to be less than VMCG because engine failure below VMCG means the aeroplane is uncontrollable, and the definition on V1 is that the takeoff can be continued following engine failure. The rule also stated that V1 must not be greater than VMBE. Again, this makes sense because at V1 the aeroplane must be able to stop or continue the takeoff. But above VMBE, it's impossible to bring the aeroplane safely to a stop. Let us look at the scenario where, due to high density, the value of VMCG is higher than the idealized V1. In this case, takeoff is prohibited. However, this problem is solvable. The chosen V1 can simply be increased until it is equal to or more than VMCG. However, notice that the accelerate stop distance increases, the takeoff distance decreases, and more importantly, the total field length required increases. So long as the runway is as long as the total field required, then moving V1 to this point is not a problem. Hopefully, by understanding this graph, you are able to see the consequences to the required distances should V1 need to be moved from its ideal or balanced position due to either pressure from VMCG or VMBE. The speed VEF is a rather strange one. As per the certification specification definition, VEF means the speed at which the critical engine is assumed to fail during takeoff. VEF is selected by the aeroplane manufacturer for purposes of certification testing, primarily to establish the range of speeds from which V1 may be selected, and secondly, to help determine the accelerate stop distance required. Let us try and explain what VEF is all about. The definition of V1 is the speed at which, if the failure of the critical engine was recognized, there is sufficient distance remaining to either abandon the takeoff or continue the takeoff. However, recognizing that the engine has failed does take time. In fact, it's about 1 second. Therefore, to recognize the engine failure at V1, the engine must have failed about 1 second before V1, the speed at which the critical engine failed, so that it may be recognized at V1, is called VEF. So far we have seen a sequence of V speeds in the takeoff that starts with VMCG, then VEF, 1 second later V1, and lastly VMBE. More will be added to this list as we work through the rest of the V speeds. The speed VMU is defined as the minimum unstick speed. VMU is the slowest calibrated airspeed at which the aeroplane can safely lift off the ground and continue the takeoff. However, despite VMU being the lowest speed the aeroplane can safely lift off the runway, in actual operating conditions, the aeroplane does not lift off at this speed. The aeroplane is flown so that it actually lifts off at a slightly faster speed. The reason is because VMU is very close to the stall speed, and the aeroplane controllability is very sloppy. And lastly, in order to actually lift off at VMU, some fairly dramatic actions take place, which may be uncomfortable for the passengers, as shown by the image on the screen. It may seem strange, but the aeroplane is actually able to lift off at a speed where lift is less than weight. The reason being because so long as the nose can be raised to a high enough attitude, then there is a vertical component of thrust, which, together with lift, balances weight. The amount of this vertical thrust is controlled in part by the amount of thrust generated, but also by the amount of nose-up attitude the aeroplane can attain. This nose-up attitude may be limited by the power of the elevator to push the tailplane down, or by the tail itself striking the runway, in what is described as a tail strike. Hopefully now you are able to realize why it is unwise in operational conditions to lift the aeroplane off the ground at VMU. The actual speed the aeroplane will lift off in operational flights is called VLOF, and we will discuss this speed next. VLOF means the liftoff speed. VLOF is the calibrated airspeed at which the aeroplane first becomes airborne, which is at the moment when the main wheels have left the runway. VLOF should be faster than the minimum unstick speed VMU. The margin above VMU is determined by several factors. For example, VLOF must not be less than 110% of VMU in the all engines operating condition and 105% of VMU in the one engine inoperative condition. However, if the attitude of the aeroplane in obtaining VMU was limited by the geometry of the aeroplane, i.e. tail contact with the runway, VLOF must not be less than 108% of VMU in the all engines operating condition and 104% of VMU in the one engine inoperative condition. Returning to our construction of the sequence of V-speeds in the takeoff, we can now add VMU and VLOF, as shown.